what we want to do is take a few instances where we're translating observations into differential equations, like we did in this population equation. The rate at which a population grows is proportional to the size of the population. That's just a hypothesis on what, creating a description of the population that we see. So we want to be able to translate observations into differential equations to get an idea about how things are working. So here's another example. Acceleration due to gravity is constant. Acceleration due to gravity is constant. This is a statement about a rate of change of a rate of change. And we're saying that this quantity is constant. So here's the statement that we're making. Acceleration is constant. Acceleration is the rate of change of velocity that's supposed to be a prime. And velocity, in this case, since I'm saying due to gravity, we're going to say that velocity is the rate of change of height. I should really write this. Prime is terrible notation for this. Sorry, Newton, but your notation is kind of bad. We're going to use Leibniz right now. So if we say that this is a description of a function for a height, so saying acceleration due to gravity is constant is an observation that we might make, and it involves a derivative, a function and its derivatives. So the height of an object, the derivative of the height of the object with respect to time will be the velocity of the object, and the derivative of the velocity of the object with respect to time will be the acceleration of the object, and we're saying that that is going to be constant. So we're saying that the second derivative of the height is equal to some constant. So if the height, let's say, is h of t, so if h of t is the height, then the derivative, h prime of t, is the velocity. And the third derivative is the the second derivative is the acceleration. Height, velocity, acceleration. And what we are saying is that the acceleration is constant. So we're saying that h double prime is equal to some constant. I'm going to call the constant g for gravity. That's our observation turned into a differential equation. This is a description of how high something is going to be based on our observation. So we've got our observation up here, and here's our equation translated, our observation translated into a differential equation. So we translated our observation into a differential equation. Now, the handy thing with this particular example, this is probably the most common first example in differential equations, is that we just said the second derivative is this constant, so we can actually work backwards to write an equation for the height. We can solve this by integrating twice. So note, we can solve this differential equation by integrating twice. So that's one of the reasons that we like this particular differential equation. We're saying that the second derivative is this constant. So I'm going to integrate both sides with respect to t. So the first derivative, g is just a constant, so will be g times t plus some constant. This is where it's going to be very important to write the constants of integration, because we're going to be integrating again. So now we'll integrate again h double prime of, oops, I went the wrong direction, h of t. If we integrate again, we get 1/2 gt squared plus c times t plus another constant of integration. So I'm going to call this c1, and we get another constant of integration, c2. So here is a function that would describe the height of an object. If we take the derivative, we get the velocity of the object at any time t. And if we take the second derivative, we end up with the constant, which is going to represent the acceleration due to gravity. Any questions? All right. Normally, we assign upward velocities to be positive, and we know that gravity will work against an upward velocity. So normally gravity is some negative number. So normally we measure upward velocity as positive. So normally we list gravity on Earth as negative 9.8 meters per second, and also negative 32 feet per second. So these are the two numbers that we need to remember representing velocity. These are going to be negative because gravity is going to want velocities to go down. Gravity wants negative velocities. So we have some initial upward velocity, that velocity will decrease. In this setup, where g is going to be one of these numbers for representing velocity, the first number we come across here, c1 is going to be whatever velocity you have when t is equal to 0. That's before gravity has taken hold. So c1 is your velocity at time 0. And that means c2 will be your height at time 0. So your initial velocity and your initial height. So that gives us two height functions. We can have negative 9.8 divided by 2 is going to be 4.9 t squared plus v0 times t plus h0, or negative 16 t squared plus v0t plus h0. So these could be your equations of motion. Or something is being subject to gravity on Earth. Any questions? What we're ignoring when we set this up is when we say that acceleration due to gravity is constant, we are ignoring air resistance. So if you're in physics, when you're in physics class next semester, a lot of times you're going to start off by ignoring air resistance. You're also going to do things like ignore friction, which is, I guess, maybe the same thing. Maybe it's different. Physics people, correct me. Oh, you're not in physics yet. Win. I can say what I want. I'm just kidding. So normally you start off with the simpler problem of not worrying about air resistance and not worrying about friction. That simplifies the problem. You get to complicate the problem later, so don't worry. Any questions on dropping things off of buildings? All right, let's pause the video here and talk about next steps.